Hi, I'm Alex doing Alex Things, and I'm starting a little video series on just some basic components as I learn how they work. Today I want to talk about the LM317, which is a positive adjustable linear voltage regulator. You can see one here. It's just 3 pins. I added a heatsink on this. This is a TO220 package. You can see here, one of these guys. Don't worry about this, I'll explain all that in a minute. So the LM317 has 3 pins. Your first pin is adjust, second pin is V out, and third pin is V in. The LM317 has an adjustable range from 1.25 volts all the way up to 37 volts. I mean, assuming you're supplying enough voltage for that, because these things, they work by basically dropping the voltage that you're supplying into V in to get you a regulated and stable V out. And that 1.25 volts to 37 volts is a differential. This regulator is floating, so it's not really referenced to ground. So the max differential that you can have between V in and V out is 37 volts. They do make a high voltage version. I think it's called the LM317HV, and I think it goes up to 60 some odd volts. And as I said, these work by dissipating the difference between V in and V out as heat, which is why you need heat sinks on them, usually. You set the voltage out by using a voltage divider. Here's those 3 pins. R1 in the data sheet, you're typically using 240 ohms for that. And the way that it works is the LM317 inside here, it creates a internal voltage reference between the adjust pin and the V out pin. And that voltage is always 1.25 volts. So when you're setting your voltage output, it's going to be 1.25 volts plus whatever this resistor is going to develop over it. And that gives you your V out. The V ref, that 1.25 volts, it is very small. I read in the data sheet it's anywhere from, I think it was 50 to a maximum of 100 microamps. And that's going to be flowing from the adjust pin to here and to ground. So that very small 50 microamp current's flowing to ground. That's kind of getting in the weeds, but I wanted to show you that because that's where this 1.25 volts VREF comes from. This is the equation given on the TI data sheet. If you ignore that 50 microamp current and you just deal with this part, it makes the formulas quite a bit easier. Now, before I continue on, I thought this was a good spot to just stop. And in the data sheet, they give you a functional block diagram of the LM317. I kind of tried to redraw it so it's laid out the same way that the pins are actually laid out. But the internal voltage reference is developed here. And keep in mind, I haven't learned how to use op amps yet. I just learned a little bit for this video to try to teach myself what's going on here. I think this is right, but take it with a grain of salt. Anyway, so the 1.25 volt Zener creates this 1.25 volt signal on the non-inverting input of this op amp. That the op amp is going to try to make these two inputs equal. And because you have negative feedback here, and I think it's configured in what's called a buffer configuration. But anyway, so you got 1.25 volts coming in here. It's going to drive these this Darlington transistor, these two, to try to create 1.25 volts on the other input. And so it's going to, so the main power flow is coming from V in through here, up through here, through these transistors, and back down to V out. Of course, down here you're going to have, if you're doing a voltage regulator, you're going to have the 2 resistors, R1 and R2. And if you're doing a current regulator, you're just going to have R1. I'll talk about that kind of towards the end of the video. It wasn't the main point of it, but I just kind of wanted to show you what the inside functional block diagram is described as. All right, with that out of the way, we can go back to the formulas. So if you want to find your voltage output, you just do 1.25 volts times 1 plus R2 over R1. And then if you know what V out is, what you're angling for, and you also know what R1 is, right? Because they say to typically use 240 ohms for R1. Then you can just simply plug in 240 here and whatever your voltage desired output is here, and then solve for R2. And then, of course, if you wanted to solve for R1, you just move things around and you get that. Now, what's going on here, let me show you this first. So I try to color code this, but then I got excited because I have a bunch of these voltmeters from Harbor Freight that I got a while ago. They don't last too long, but they're kind of fun to use. Anyway, again, here's your voltage divider, and that's how you set your voltage output. In the data sheet, they do suggest using a capacitor on your input to ground and your output to ground. And the reason you want these, I guess, is if you have a moment where you're drawing a lot of current or something, it kind of helps stabilize the input and the output. I've successfully done it without the capacitors, but I usually always add them just in case. I went through and I made a couple, I call them scenarios, but I just did, a different voltage in and different voltages out, kind of what things should look like ideally using those formulas I was showing you. So in this case, we'll have 15 volts coming in on pin 3 and 10 volts coming out on pin 2. So the first thing you want to do is you want to set up your voltage output, figure out what resistors you need. Again, R1 is basically already decided for us because the data sheet says a value of 240 ohms is pretty ideal for that. So we'll leave that at 240 for R1. You rearrange that, and then you're just solving for R2. You plug that in, so 240 ohm R1 times 10 volts out divided by the 1.25 volts Vref minus 1. You do that, and you get a value for R2 that should be 1,680 ohms. As you'll see in a minute, I didn't have that, so I just put 3 resistors together. And that would give me 1683, which I just plugged it back in just to make sure it would still be 10 volts, which it was. So again, R1 is 240, R2 will be 1683, and our voltage out should be 10.0 volts. Then after that, I wanted to find the current through R1. So we just take I equals V over R. Our voltage across R1 is always going to be 1.25 volts because that is what the LM317 develops as its Vref. And so we do that, 1.25 volts divided by 240 ohms, and we get 5.2 milliamps. So at this point, I thought it would be good to just stop and go through a couple notes on R1. The current through R1 is just calculated is due to that 1.25 volt Vref. This current is a primary current through R2. Even though I adjust current flows through R2, it's too small to usually even worry about. The lower R1's resistance, the more current will flow and might be wasted. The higher R1's resistance, the less current flows, and the regulator can become more sensitive to noise and oscillations. The minimum load current in the datasheet is given as 3.5 to 10 milliamps, and this is the minimum current needed to maintain regulation. This can be accomplished with just your attached load that the LM317 is powering, or by using R1 or some combination of R1 and the load. If you use just R1 to maintain minimum load current, let's say you've got this all wired up and you don't have any load attached, then a suggested value of 120 ohms is recommended because 120 ohms, 1.25 volts, gives you a current of 10.4 milliamps. I typically use the 240 ohms for R1, and that gives you the 5.2 milliamps because I usually have a LED or something hooked up to the LM317 just to show me it's working, and that adds the load that you would need for the minimum load current, even if you didn't have anything else hooked up to it. Anyway, back to the video. Then, not that this is important, but I kind of wanted to know what's happening, so I wanted to find the power dissipation through R1. So then there's 2 ways to do that. P equals I times V and V equals I times R. Move that around. I equals V over R. You plug that back into P equals I times V, and then you get P equals V squared over R, and you do it that way, and you get 0.007 watts through R1, well within its limits. Or if you want to just simply use the power formula and use the current we already calculated, again, 0.007 watts through R1. Now you want to find the current through R2, this guy here. Before we do that, we're going to need the voltage across R2. To find the voltage across R2, it's going to be dependent on both V out and the 1.25 volt reference. So we have V out minus 1.25 volts gives us the voltage across R2. So you do 10 volts, because that's what we're angling for, 10 volts out here, minus that voltage between the adjust and V out, 1.25 volts, and that gives us 8.75 volts across R2. So we should be measuring 8.75 volts across here. Then the whole point of this is to find the current. So to find the current, I equals V over R. I equals 8.75 volts over 1683 ohms, because that's what our resistance is. And we get 0.0052 amps or 5.2 milliamps. Again, same thing as that. Right, so now, then what I did, now we need to find the power dissipated through R2, just like we did for R1. You can either do it as P equals V squared over R or P equals I times V. In both cases, you get 0.045 watts through R2. Then for the power dissipated by the entire LM317. Since we don't know the current that's demanded, we can't really do this, but let's just assume we're demanding 100 milliamps, so you'd have 0.1 amps times some voltage. And that voltage is the delta between the voltage in and the voltage out. So in this case, it'd be 15 volts minus 10 volts times 0.1 amp, which gives us 1/2 of a watt must be dissipated by the LM317. Because remember the way these things work on the inside is you're taking the voltage in and you're dropping it to a regulated voltage out. That has to go somewhere. It's dissipated as heat. Okay, now that we've done our basic calculations, I can show you what's going on here. So on the left here, voltage in, that's simply coming from my my wall power supply. I have a variable power supply that I'm using to power the breadboard. So that's the voltage in, 15 volts. That's being applied to pin 3. Then pin 2, V out, that's what this meter is measuring. Then V ref is measuring the difference between the adjust and the V out pin. And we talked about that should be 1.25 volts difference between here, which is going to be the voltage across R1. And we have 1.23 volts, which is pretty close. Then over here we have 2 meters measuring current. This first one here, the digital meter, it's measuring the current from here, it's basically right here, to ground. So it's measuring the combined current of R1 and R2, which it's reading 5.4 milliamps, which we calculated that R1 should be 5.2 milliamps and R2 should be 5.2 milliamps. The only additional current to this would be from this meter, which is measuring the microamp current flowing from the adjust pin through R2 to ground. But it's so tiny, it's really negligible. This meter is currently set to 0.5 milliamps at full scale, and we're reading about 50 microamps here. We could go one more notch sensitive, so full scale will be 50 microamps. And you can see it goes full scale, so we do have, in fact, 50 microamps flowing from the adjust pin through R2 to ground. Switch that back. These linear voltage regulators, they have to have, and I think I mentioned this earlier, I think they call it headroom. You need to have a certain voltage above what your regulated voltage out is in order for this thing to maintain regulation. The data sheet says, I believe 3 volts. I found it's roughly around 2-ish volts. So I'm going to go ahead and vary the voltage input. I'm going to bring it down, and we can see at what voltage in the voltage out starts to fall apart. So we're at 14 volts, everything's still stable on V out. 13 volts, we're still okay. And we're 2.5 volts above V out, and it's starting to look like it's struggling a little bit. Now we're at 12 volts. Actually, it looks okay. Okay, so that's a 2 volt headroom, and we'll keep going down. And right there, at about 1.5 volts, it kind of starts to fall apart. As you can see, V out now is just continuing to drop as I'm continuing to drop V in. V ref is starting to drop. Our currents are coming down. I'll go all the way down. That's as low as my power supply will go, 2.3 volts. And we'll come back up. All right, so at about 11.5 volts, so about 1.5 volts above what our V out is supposed to be, it's back on stable regulation. Now that could be due to how much current you're demanding. So let's say if you're demanding, the full, 1 or 1.5 amps that the LM317 can produce, which you should definitely be using a big heatsink then. But if you're doing that, I'm guessing that the 3 volts that's in the data sheet on the minimum differential needed to maintain regulation, that probably becomes important, but I don't know. Anyway, so as we go well above 15 volts, I think this goes up to 19 or 20 volts. You can see even at, 19 volts. Even at 19 volts, we still have a stable 10 volts. I don't have enough meters to show you one other voltage, so I'm just going to switch this out real fast and we'll come back to it. All right, so I pulled this out of measuring current, and now I've just got it set to 10 volts. So now what I want to do is I want to measure the voltage across R2. We calculated it should be 8.75 volts from ground to this junction here where you've got the adjust coming in, which is this right here, which is right between R1 and R2. I just stuck some tape over it just to make it more clear. I'm going to have to pull this tape off though to see it. I had to just stick a couple resistors together to get that resistance. So keep in mind this is R2. We should have 8.75 volts across it. And it's the analog meter. I guess I probably should have chosen a digital one, but whatever. Okay, so from essentially ground to here. So we're right between 8 volts and 9 volts. So we're at about 8.5 volts on this meter. Let's see. If we're at ground, I can just stick that there and hold that closer to the camera. Okay, so we're just above 8.5 volts, which is in agreement with what we calculated. Okay, so now if you want a adjustable voltage regulator where you can continuously adjust the output voltage, V out, all you do is you replace R2 with a variable resistor potentiometer. And in this case, so I didn't have a 5K potentiometer, unfortunately. I only had a 10K. So what I did for R2 is I took a 10K potentiometer and a 10K fixed resistor, put them in parallel. And as you know, that should, when this is at 10K ohms and this is at 10K, it should drop to 5K. Obviously, I don't think this will stay, linear throughout its whole range, but I mean, it gets me close enough and allows me to show you this. So if we adjust this all the way up to the maximum of 10,000 ohms, the resistance across here should be 5K. So we're just checking. With these analog meters, you've got to check to make sure that they zero out. when you're doing resistance measurements. So it's at 0. Okay. And we're on the times 100 scale, and it's at the very top. So it's reading 50, so we're at 5,000 ohms. Now, let's see if I can do this on camera. If I hold that there, so when we had 10 volts out, now that was with a resistance for R2 of about 1700 ohms. So I'm going to go ahead and bring this resistance down to about 1500 or thereabouts. So right about there. It should be about 1500 ohms between the two of these. So when I power this on, we should have about 10 volts. Might be a little higher, might be a little lower. I don't know. Okay. Get this out of the way without messing anything up. Let's hook this adjust pin back up and apply power. Okay, so we're at 11.2 volts. So I overshot it a little bit. Okay, so there's where we left off. 19 volts in, 10 volts out. So now what you can do is you can just simply turn this potentiometer and you can adjust the V out. That's as low as it'll go. So our lowest we can get is 1.3 volts. And you can turn this back up. It looks like the highest I can get, I was messing with this a few minutes ago, is around 17 and a half. Yeah, around 17 and a half. Then the V reference starts to change. As you try to force it higher, it won't go any higher. Your V ref changes and the current starts dropping. So V ref goes low and your current starts dropping through R1 and R2. And it won't really go much higher than 17 and a half volts if your input is 19 volts. So that's how you make your voltage regulator adjustable. The main point of this video is to go over voltage regulation, but in the data sheet it does show that you can use the LM317 as a current regulator, so I just wanted to go over that real quick. The biggest difference is R2 is omitted altogether and you're taking your output after R1 in this case. So in order to get this constant current output, you're going to size R1 according to this formula. So I output equals V ref over R1 plus I adjust. I adjust, as we talked about earlier, so small, can omit that. So your output current is going to be equal to 1.25 volts, which is that reference voltage, divided by R1. And if you solve for R1, you get R1 equals 1.25 volts divided by I output in amps. So in this case, I wanted 20 milliamps output. So R1 is equal to 1.25 volts divided by 0.02 amps, 20 milliamps. And that's going to give us a value of 62.5 ohms is what we're going to need for R1. I only had two 33 ohm resistors, so I just plugged it in for 66 ohms. In which case that I out should be around 18.9, 19 milliamps. That's what we should expect. And then the power dissipated across R1 is going to be P equals I times V. If you plug those numbers in, you get 0.02 watts. And again, it's 1.25 volts because that's what's developed across R1 between I adjust and V out. So well within the limits of my little quarter watt resistors. A quick note when using the LM317 as a current regulator for R1, all the current that's flowing through the regulator and out to whatever you're powering is going to be flowing through R1. Now this current should only be at 1.25 volts, but it's still important to consider this in R1's power handling. So for example, using the power formula, if you have 1 amp of current and it's at 1.25 volts, you're going to have 1.25 watts. So you're going to want to make sure you size R1 accordingly and consider its heat production. So just like last time, this measures V in, this measures V out, this measures the difference between the adjust pin and the V out pin, and this one here is going to be measuring the milliamp output. You've got the supply going to V in, then this is coming out of V out to this resistor, these two resistors that make up the 66 ohms for R1. This yellow wire is going back to the adjust pin, just like in the diagram. Then we're taking our current output along this blue wire and it comes over here where this current meter is going to measure it. So let's apply power. Now remember, we should be getting 19 milliamps on the output, which we do. So we've got 19 milliamps out. Our Vref is about what we'd expect. V out is 1.28 volts and V in is 19 volts. So that's how you make a constant current source with the LM317. I'm sure you can get a lot more fancy with it than just this, but that's how you do it. I'm just going to add this little bulb here just to see what happens. It's just a little incandescent bulb. Alright, let's apply power. And we still got 19 milliamps. Bulb's lit. And we can see V out increased from, I think it was like 1.2, something around there, to 5.2 volts. And that's how you use a LM317 as a constant current source. I hope this video going over the basics of the LM317 helped you. As I mentioned, I plan to make more of these basic type videos as I teach myself more about various components. Please like and subscribe if you want to see more of these kinds of videos. And as always, may the Lord bless you and keep you. May the Lord make his face to shine upon you and be gracious to you. May the Lord lift up his countenance upon you and grant you peace. By the power of the Prince of Peace, Yeshua. Amen. See you guys. Shalom.